Okay, I'm really excited to be here. Today I'm going to be talking about our recent paper on complete knowledge, preventing encumbrance of cryptographic secrets. Oh, there's my clicker. So cryptography models a very simple form of knowledge. So what does this mean? If Alice knows some secret key SK, she can sort of explicitly furnish it as private input to a protocol and vice versa. So if you think about crypto functionalities, for the most part, you can think about them as being, say, a keyed functionality with some key SK that takes an input and produces an output. So this sort of talk will think about what happens with this secret key, instead of being held by Alice, is actually held inside of a trusted hardware box. So for the purposes of this talk, you can think about trusted hardware as sort of a black box that can run some predefined program and provides confidentiality and integrity of the output and running of the program. So in this case, if the secret key is held inside a trusted hardware, such that Alice doesn't know it, the TE can still sort of take part in the same crypto functionality. And this, as it turns out, is a problem, and I'll mention this in my talk. So basically, this is the problem of what we call key encumbrance. So in a nutshell, the idea here is to expose not the secret key itself, but a partial computational functionality of the secret key. So what does this mean? If you think about some sort of crypto functionality that uses the key, instead of it being held by Alice, let's say it's held by the trusted hardware here, let's say Intel SGX. So you can think about sort of the interaction with this keyed trusted hardware as providing an input to the program and getting an output that's based on the key in the input. But what if the SGX, trusted hardware, only responds to approved inputs? So there's a program that's running inside of the trusted hardware that only responds to approved inputs. This is what we'll call key encumbrance. And it turns out that it's not easy to identify key encumbrance. So for example, if Alice has her own key, she can sign all messages in existence. But let's say there's a program running inside a trusted hardware which actually controls the key. The hardware can block signing of a message for just one message, say hello. And it's not really easy to identify which one of these two scenarios we're in. And in fact, proofs of knowledge don't actually work because the same proof of knowledge protocol can be executed inside the trusted hardware itself. So for example, a simple proof of knowledge would be signing a random message with the secret key, but you can think about the same program, same protocol being run with the secret key inside trusted hardware as well. And in some sense, the motivation of this talk is that encumbrance allows you to prove knowledge without actually owning or knowing the secret key. And our paper introduces what we call proofs of complete knowledge, which will show unencumbered, complete access to ownership of the key. And in general, this encumbrance will also be for something like multi-party computation, not just trusted hardware, but I'll focus on trusted hardware in this talk. So before I get into complete knowledge protocols, I'll first describe why it's important to prevent against these key encumbrance by showing some attacks based on this. So the first one I'll show is trusted bribery, and this is the main one I'll focus on. So let's say we had a trusted hardware box that owned a key, and this key allowed a user to vote. But it had a program installed in it that said, for this election, I only will sign messages that allow me to vote for blue and not any other color. But it will allow all sorts of other transactions, including potentially transferring out cryptocurrencies, tokens, whatever else sort of the user wants to do with the key. Now, this sort of encumbered key program creates a problem, because here you can think about the key as Alice's key, but she doesn't own the key. But she can still do everything she wants with the key. She doesn't care about this particular election and is willing to be bribed for it. But she can still do everything else that she wants with the key. But at the same time, the briber is guaranteed that Alice cannot vote for anything else other than blue. So this sort of encumbrance creates a trustless bribery between a briber and the user who wants to be bribed, so that they don't have to trust each other, but can still benefit from the transaction. And in fact, the highlight of this paper is that there's been a long line of work on so-called coercion-resistant protocols, and they all break because of this key encumbrance attack. And I'll refer you to the paper for more details. So in general, you can think about this sort of trustless bribery as being expanded in the sense that briber can buy votes from a lot of different users using the same sort of encumbrance mechanisms. But what's even worse is we define something called a dark DAO, which is sort of like a vote-buying marketplace, if you will, where users who want to sell their voting power or even some minimal access to their keys can interact in a marketplace with buyers, or vote buyers here, who want to bribe these users to buy their votes. And sort of this marketplace allows selling votes to the highest bidder. And in fact, this is a dark marketplace in the sense that the voters and the vote buyers don't actually even need to know each other. And this was actually first noticed a few years ago, and the term dark DAOs was coined in this sort of seminal blog post by Phil Diane and others. But sort of the practical relevance of these kind of dark DAOs was brought up when we actually built a prototype and a follow-up work to the paper I'm talking about, actually, which we built sort of a dark DAO explorer and a way to do these sort of bribery marketplace in Oasis. The other thing I'd like to highlight is that it's actually not just sort of Web3 style bribery and Web3 style voting attacks. You can actually think about these encumbrance as being a problem on even something like end-to-end messaging systems, which offer deniability. You can also think about encumbrance being a problem for any sort of Web2 credentials, where these credentials can be sort of bought and sold or rented out. For example, selling the ability to tweet from a specific account, or password sharing, things like that. And I'll refer you to the paper for more details. So sort of the central question of this work is, how can we detect this sort of encumbrance and establish individual ownership, which standard proofs of knowledge don't actually give us? And so this is just a meme I'll leave you there, is like what we want is complete knowledge. So kind of let's try to take a step back and understand, why don't these standard proofs of knowledge work? So first, some background on proofs of knowledge. You can think about proofs of knowledge as an interactive protocol between a prover and a verifier, where the prover here wants to convince the verifier that she knows some secret. For example, the secret key corresponding to a public key that's known by both parties. So more generally, you can think about this as some statement X that's public, and you want to prove that Alice, here the prover, knows some secret witness W, such that f of x comma w equals 1. So most commonly, this is sort of an NP relation. But for all intents and purposes, you can also think about this as just secret key corresponding to public key to build intuition. So typically, proofs of knowledge have a couple properties that they need to satisfy. One of them is completeness, which you can intuitively think about as an honest prover who knows this witness W can always convince the verifier. The second one is soundness, where a cheating prover who does not know this witness should not be able to convince the verifier. And for proofs of knowledge in particular, you can think about a property called knowledge soundness, which subsumes the earlier soundness version, in the sense that if the verifier was convinced, then there is an efficient extractor device that can sort of extract the witness from the prover. So this sort of is the way typically knowledge is modeled in cryptography, through this extractor machine that can run on the prover and extract out the witness. And just as a sidebar, proofs of knowledge don't need to be zero knowledge, although they can be. So sort of trying to understand where these definitions fail, the kind of stark revelation here is that the extractor is often a theoretical proof construct. So what does this mean? So for instance, in most cases, it gets sort of code access or oracle access to the entire prover machine. And this actually may not be practically instantiable. So for example, if the key is held inside a trusted hardware box, if it's tamper-proof by assumption, the extractor should not be able to extract out the key from the trusted hardware. So essentially, this extractor that makes the theoretical proof go through cannot be instantiated in practice and won't be able to extract from this trusted hardware box. So in some sense, for our proofs of knowledge, we want our extractors to be concretely instantiable. They want to be practically runnable. So intuitively, we want some physical entity that should be able to recover, reconstruct the entire witness. So for the very least, we want sort of these straight line extractors, which means they should not be able to rewind the prover. And we also want sort of non-programming extractors, so they should not be able to program the random oracle, which is, again, sort of a theoretical construct that may not be practically instantiable. So this brings us to our definitions of proofs of complete knowledge. And the idea there is we need to make sort of these hardware-based assumptions. So we formulate this resource-based formalism with these hardware-based assumptions. And the reason we need to do that is you can think about everything that you can do outside of trusted hardware as being able to do inside of trusted hardware. So without hardware assumptions, it may not be possible to distinguish where the key is held at. Another way you can think about this is anything that you can do by a single computer, you can also do in multi-party computation or MPC. So again, you may not be able to distinguish just in the plain model, which is why our modeling will rely on these sort of hardware assumptions. So the key idea in this model is to physically instantiate the resource from basically the part of the protocol that enables the knowledge proof to go through. So we have a resource functionality R here that's connected to the prover, who is interacting with the verifier in this proof of complete knowledge protocol. And the extractor, instead of being a theoretical construct, is now actually thought of as an eavesdropper, man-in-the-middle entity that's modeled on the channel between the prover and the resource. So the idea here is that if the extractor learns the secret, then the prover or any machine that has access to this communication channel will have complete knowledge of the secret. So again, here the key observation or the key modeling insight is instead of having the extractor be a theoretical proof construct, we have it be modeled as a man-in-the-middle channel between the prover and the resource, as a concrete entity in essence. So I'll now define some proof of complete knowledge properties that we want to satisfy. The first one is, again, completeness. And the way we define completeness is that the honest prover can convince the honest verifier using an approved resource, R belonging to some approved resource set. And essentially, this sort of models the fact that these approved or honest resources will allow this channel E to extract out the secret. The second property is the more tricky one, which we'll call CK soundness, or forced revelation. And the idea here is that no adversarial prover should be able to convince an honest verifier using any practical resource. So not just the approved ones, but any unapproved ones as well, as long as they're sort of practically instantiable, without this extractor machine being able to recover the witness. So this sort of instantiable or practical resource set essentially will formalize our hardware assumptions for the protocol. And you can kind of observe here that the forced revelation also implicitly says that some honest resource will be necessary to provide complete knowledge. And so any proof that will go through will have the extractor being able to extract out the witness in practice. So I'll sort of describe two protocols for complete knowledge. The first one will be based on trusted hardware itself, so sort of a fight fire with fire kind of situation. And the second one I'll describe will be a proof of work based solution. So I'll get into the first one, which is the trusted hardware based solution. And here you can think about the honest resource as the SGXTE as a physical instantiation of a trusted party itself. So kind of this is the diagram here. You have a prover, again, you have a verifier, and the prover is connected to this SGX resource. And the SGX runs a very simple program for the complete knowledge proof. It just asks the prover to input the witness in plain text, checks the correctness of it, and just signs a message using its master secret key that it's seen the correct witness. And now the prover can take this proof and send it to the verifier, who can verify it, as I'll describe. But the main observation here is that the plain text channel between the prover and the resource will allow the eavesdropper on this channel to extract out the secret witness. So essentially, this relies on the fact that the input into the SGX will be given in plain text rather than in any encrypted channel. The verification is very simple. You can use this remote attestation functionality of trusted hardware in order to verify that the program running inside of the trusted hardware is the CK program. And then you can verify the signature of the trusted hardware using the master public key. And sort of the hardware assumption that's necessary for this plain text channel intuition is that the SGX cannot be sort of simulated inside of another SGX. Because if you could do that, you could imagine the outer SGX sort of encrypting inputs outside of it and then decrypting inside of it and then sending it to the inner SGX. So which would violate this plain text channel assumption that could be eavesdroppable. So this is where our hardware assumption for our protocol will come in, but as long as you cannot have a SGX simulated inside another SGX, this protocol will be sound. The second protocol I'll describe is an ASIC-based one. So the core idea here is that we'll take a well-known common proof of knowledge protocol, which is a Sigma protocol, and we'll sort of embed its transcript into a proof of work mining puzzle. And I'll describe what that means. So here, the honest resource you can think about as a proof of work mining ASIC, which again will take inputs in plain text. And sort of any form of encumbrance using trusted hardware or MPC will be slower than ASICs. And this is sort of the hardware assumption we'll use for this protocol. So hash computations on an ASIC will be orders of magnitude faster than any sort of trusted hardware-based or MPC-based CPU or GPU computation. So let me describe a little bit about this protocol. So first, for background, I'll describe Sigma protocols, which is a common three-round proof of work, common three-round proof of knowledge of some witness W for a statement X belonging to some language. So this three-round protocol has the first round as a message from Alice, the prover, to the verifier, which has a commitment A. Then there's a challenge phase, which is a response from, there's a challenge from the verifier to the prover. And finally, there's a response from the prover back. So it's sort of the general structure of a three-round Sigma protocol. And the Sigma protocol transcript here, which will be important for our protocol as well, is sort of just the tuple A, C, S. And the property that we'll use from these Sigma protocols is a special soundness, which essentially means that you can extract out the witness from two of these transcripts that have the same commitment. So the same A here, but different C and S's, you can still extract out the witness from these two transcripts. So this is a property of special soundness that's satisfied by a lot of these Sigma protocols. So just for intuition purposes, you can also think about one common Sigma protocol is just a proof of knowledge of the discrete log. So essentially, the witness here corresponds to the discrete log of some group element, and the Sigma protocol will prove knowledge of this witness, which is the discrete log. So how does our ASIC-based protocol work? So as I mentioned, there's a prover, there's a verifier, and the prover will be connected to this ASIC resource. And now the intuition is you will take this Sigma protocol transcript ACS and sort of do a proof of work mining on it so that the hash value of this ACS with some nonce is smaller than a target value. And again, the intuition here is that this channel between the prover and the resource ASIC is in plain text, so that can be eavesdropped by our physical instantiation of the extractor. There is a little bit of a pickle here. So if you remember, there's the special soundness requires 2 transcripts for extraction. So you sort of need 2 transcripts to be on the channel between the prover and the resource. But the proof should only contain one of these transcripts sent to the verifier. Otherwise, the verifier would also be able to recover the witness, which we don't want to happen. So the way we get around this is we use the verifier randomness. Remember, from the 3-step Sigma protocol, it's the second step, which is the challenge step, that generates the randomness. So we, instead of just using that directly in our proof of work, we will sort of generate many of these Sigma protocol transcripts using the same randomness. So let me kind of describe the protocol a little more detail. The first step you can think about as the same as the Sigma protocol. You just have a commitment A. For the second step, the verifier generates some randomness R and sends that over to the prover. But instead of using that R directly, the prover gets the ability to choose a nonce mu to get challenge C by just computing the hash with the randomness. And then based on this, it will compute the third response, which is S in the Sigma protocol. And it will use this transcript now to mine again the ASIC proof of work puzzle such that the hash is smaller than some difficulty level. And the way this C is chosen is such that with high probability, at least 2 C's will be required to find the proof of work solution. So let's say the prover chooses 1 nonce, gets a challenge and a corresponding response. With high probability, if it tries to brute force through all possible nonces for the proof of work solution, it won't be able to find a valid one. It will have to sample a second sort of this bigger nonce to get another C, S, and then try again with the proof of work mining. So this is sort of the thing that will allow for the extraction within the channel between the prover and the resource by our extractor E. And finally, when such a solution is found, you can just take that one solution and send it over to the verifier. So the solution here consists of not just the Sigma protocol transcript, but also these 2 nonces, U and V. And now what the verifier does for verification purposes is it can verify the validity of the Sigma protocol transcript and also the proof of work mining puzzle, and also verify that the proof was submitted in some parameterized time tau. And remember, this is where the hardware assumption comes in of the ASIC being able to compute the same hashes significantly faster than sort of any encumbered trusted hardware or MPC. So we will have this be sort of a timed protocol in order to have the honest prover with the ASIC being able to satisfy the proofs, but an adversarial prover without the ASIC not being able to do so. And you can run the same protocol for multiple rounds in order to decrease the soundness error. So you can look at the paper for more details on the proof, but essentially there's sort of 2 errors that we need to bound. One is the completeness error, which is the probability of the honest prover with an ASIC not finding a solution in that given time. And the soundness error, or the forced revelation error, which can fail in one of 2 ways. One is the adversary uses the ASIC, but somehow only requires 1 challenge C to succeed. And the other one is if the adversary uses a network of many CPU machines and successfully computes the proof of work. So we can sort of bound the errors of this protocol by running the protocol for some theta of the security parameter rounds. We can bound the error as being negligible in the security parameter. And the paper also contains sort of concrete parameterizations that can be useful for practical deployments of this protocol. So we have a couple prototype implementations. So the first one, for the ASIC, we implemented a verifier as a smart contract on Ethereum, and we parameterized it to work with the 12-second block times on Ethereum, and also with old ASIC hardware, which still turns out to be significantly faster than even thousands of machines running a CPU. We also sort of implemented a lightweight version of our TE-based solution on Android devices. So instead of using SGX, which may not be commonly available to all users, this uses sort of the Android phone TEs for the same purpose. I'll also briefly mention some new applications that are made possible only because of these proofs of complete knowledge that would not have been possible beforehand. So the first one I'll say is key coupling, which is this is the idea of proving that two keys or two addresses belong to the same entity. And this can be useful for all sorts of things, like proving I own two accounts, so that if I transfer between these two accounts, it's not taxed as a transfer. Right? Or things like KYC diligence, where I can prove that these are all the accounts that I own. And you can kind of see here that you can't do these proofs without our notion of complete knowledge, because you could have the situation where two different parties own these two different keys and use multi-party computation to complete the proof. So you can't have a key coupling proof without our notion of proofs of complete knowledge. The second thing you can think about as a new application is what I'll call atomic assets, which are non-fractionalizable or single owner assets. And you can think about use cases for these as blockchain representations of real world assets, like houses or concert tickets. You want them to be owned by a single person rather than being owned by multiple people. And you can sort of use our proofs of complete knowledge, again, to prove things like these. So I'll leave you with a couple takeaways from the talk. To summarize, our paper shows that encumbrance can create problems for a lot of these cryptographic protocols by violating assumptions about what it means to own a key. And our notion of complete knowledge provides a solution by enabling proofs of individual ownership. And the takeaway, one sentence here, is that if your protocol doesn't use CK, it actually could be vulnerable to a slew of these encumbrance-based attacks. And I'll leave it at that. I'm happy to take any questions.
Thank you, Mahimna. I think we have time for one or two questions.
Hi, Mahimna. So the key thing here is that the communication between the prover and the trusted hardware reveals the witness, right? And so one of the reasons why why the prover might use a trusted hardware is to not leak the secret key. But this seems like it might make the secret key more vulnerable to being leaked. So the prover might not want to use it. Any comments on that?
Yeah, that's actually a very good question. So sometimes for security practices, you might want to, in a sense, encumber your own key in like a hardware device so that only the hardware device knows it. And some companies actually have this security policy. And what I'll say to that matter is that in cases where these encumbrance attacks are not so much of a problem, that may be fine. But you have to think carefully about the trade-offs there. What extra defense in depth are you guaranteeing by hardware encumbering the key as like a security practice? And what are sort of the attacks that you also leave possible by the fact that the key was encumbered in a hardware wallet, and it will be indistinguishable from the key being encumbered inside a trusted hardware which runs like a general program that can encumber it further, like the functionality. So I'll just say like you have to think about the trade-offs there.
Cool, thank you.
Go ahead.
Good. Thanks, Mahimna. Very, very clear, simple, powerful idea. I really, really love this. I have maybe a naive question. It seems like there is maybe something corresponding to designated verifier in some of these applications. So for example, the taxing authority, in order to be convinced of non-bribery, et cetera, may have to have an ASIC. In what sense are the provers essentially designated provers? Can they convince other people that everything was behaved and done properly? Or is that not too naive of a question?
So we have this notion of CK addresses as well. which basically say that once you've done a CK proof on some secret key, then it's a sense that always there will be the possibility that someone owns the key. So you sort of only need to do this proof once if you want to be convinced that somebody knows the key and it's not vulnerable to bribery attacks. So you could actually post these on-chain. And this is what we'll call, like we have our notion of CK addresses, like you can verify the secret key of an address being done in proofs of complete knowledge, and that's it, you can use that address anywhere else. With sort of the designated verifier part of your question, I'll say that actually designated verifier proofs can be broken by trusted hardware encumbrance. So you can think about a verifier whose key is inside of an SGX that accepts a designated verifier proof, and then the TE just constructs a publicly verifiable proof from just inside of, like the key inside of it, that can be, accepted by any verifier. So you can actually break designated verifier proofs by this TE encumbrance, and the only way you can fix that is by having a proof of complete knowledge that the verifier's key given to the prover in this like designated verifier proof protocol.
Cool, thanks.
All right, let's thank the speaker one last time.